Fast charging is the holy grail for battery-powered systems. But there's a trade-off. Pushing charge speeds too far can significantly shorten battery cycle life. The core challenge is to maximize charging speed without compromising long-term battery health. Solving this has wide-reaching benefits. For users, it means faster charging and fewer replacements, improving convenience and lowering costs. For businesses, it reduces downtime and operational expenses across devices, fleets, and storage systems. Reducing battery waste also supports environmental goals by easing the burden on recycling systems and raw material extraction. And at a strategic level, longer-lasting batteries mean less pressure on critical supply chains, reducing dependence on imported materials like lithium, cobalt, and nickel. The ultimate goal is clear: charging fast while maintaining long cycle life. There are two main ways to achieve this. First, we can improve battery design. It involves developing better electrode materials, electrolytes, and manufacturing methods to build batteries that can handle fast charging without degrading quickly. This focuses on the material and process side. Second, we can optimize fast charging protocols. Instead of charging at a fixed rate, we adjust how power is delivered during the charge. That means dynamically controlling current and voltage over time, based on the battery's condition, to reduce stress and slow degradation. This comes from the operational side. Let's first look at improving battery design. This is challenging because it's a multi-parameter optimization problem. You have to consider energy density, production, economy, environment, and sustainability, all at once. After meeting those requirements, you still need to maximize the cycle life. There are constant trade-offs between these factors. That's what makes it hard. This kind of multi-parameter optimization is a bit like making a great burger. When designing a burger, you have to think about multiple factors. It should provide enough calories, taste good, be healthy, be affordable, be easy to make, and use accessible ingredients. The first four, calories, taste, health, and cost, directly affect the customer experience. The last three, ease of preparation, ingredient sourcing, and affordability, are more about the business side, and sometimes factors compete. More calories and better taste might align, but that doesn't always make it healthy. That's the trade-off. Improving battery design is a multi-parameter optimization problem because every design choice affects performance, cost, sustainability, and cycle life. Optimizing fast charging protocols is also a multi-parameter optimization problem. We'll dive into that next. Let's start with how a lithium-ion battery charges. It consists of a cathode, anode, separator, electrolyte, a positive current collector, and a negative current collector. Lithium ions move from the cathode to the anode through the electrolyte during charging. At the same time, electrons flow through the external circuit, from the positive current collector to the negative current collector, to maintain charge balance. If we charge too fast, lithium ions may not have enough time to properly intercalate into the anode material, typically graphite. Instead, some begin to deposit as metallic lithium on the anode surface, a process that leads to battery material degradation over time. This is called lithium plating, a major degradation mechanism during fast charging. To achieve both charging fast and charging smart, we need to go beyond fixed-rate charging. One effective approach is using multi-step with multi-phase of current. This means dividing the battery's state of charge into different sections and applying different current levels at each step, adjusting how power is delivered as the battery charges. However, the best sequence of steps or protocol is unknown. There are simply too many possible combinations to test them all through trial and error. Finding the best fast-charging protocol is hard. It's subject to a large parameter space. We need to consider voltage levels, current limits, charging steps, power limits, thermal management, and even communication between the charger and the battery management system. The first option is to exhaust the space. We literally test every possible combination of charging steps and parameters, then pick the optimal solution based on performance outcomes. It's like making hundreds or thousands of burgers to find the best one. But what if a single burger took days to make? That's the case with batteries. Each test is time-consuming, resource-intensive, and expensive. In practice, it's not realistic. The second option is to take the shortcut. Instead of testing every possible combination, can we find a smarter path through the space? one that leads us to the optimal solution without needing to try most of them? To do that, we need help from machine learning algorithms. One study that takes this shortcut approach to the next level is titled Closed-Loop Optimization of Fast Charging Protocols for Batteries with Machine Learning, published in Nature in 2020. This work is a collaboration between Richard Bratz at MIT, Stefano Ehrman, and William Cui at Stanford University. William Cui is widely recognized as a leading figure in AI-driven battery research, pioneering new ways to combine machine learning with electrochemical science for faster, smarter battery design and optimization. In a previous video, we introduced another of his collaborations with Richard Bratz, where they used machine learning to predict battery cycle life. This time, the focus is on optimizing how we charge. The approach is called closed-loop optimization of fast-charging protocols. The goal of closed-loop optimization is to speed up the search. That means finding the best fast-charging protocol as quickly as possible. And by best, we mean a protocol that charges fast while preserving the highest possible cycle life. But current bottlenecks make this difficult, and they come in two dimensions. First, each battery takes a long time to test, often several days. So one goal is to reduce per battery testing time. This is where machine learning can help by learning from partial data and making early predictions. Second, there's a massive number of possible protocols to search through. So another goal is to reduce the number of tests we actually need to run. Bayesian optimization is used here to guide the search more efficiently. Now let's look at the research subject, fast charging protocols. This part is about defining the parameter space to search. On the screen, you see the parameter space as defined by the scientists. Each protocol consists of 6 steps, each corresponding to a different phase of the charging process. The entire space is defined by the first 3 constant current steps. These are the free variables, meaning they can be adjusted freely during optimization. Since the total charging time is fixed, the 4th step is constrained. It compensates for whatever time is used in the earlier steps to make sure the overall duration stays constant. In other words, if the first 3 steps take up more time, the 4th has to shorten accordingly, and vice versa. The 5th step is fixed. It doesn't change across protocols. And the final step is a constant voltage phase, where voltage is held steady and current naturally tapers off as the battery approaches full charge. Altogether, this setup defines a space of 224 unique fast-charging protocols, a manageable but still large set for intelligent exploration. So, how soon can they find the best protocol? It would take about 560 days to test all protocols, 224 in total, if you were to evaluate them one by one. But with the proposed closed-loop optimization workflow, they found the best protocol in just 16 days. And the result is striking. The optimized protocol delivered a 100% increase in battery cycle life compared to the worst-performing ones in the set. Let's take a closer look at the closed-loop optimization workflow. Batteries are tested using a cycling machine, which records how they perform over time. But instead of waiting for the battery to reach end of life, the workflow only uses data from the first 100 cycles. This data is passed into a machine learning model. We'll call this Model 1, which predicts the full cycle life based on early performance. That prediction becomes the input for the next step, Bayesian optimization. In the diagram, each cube represents one possible fast-charging protocol. All the cubes together form the entire search space of protocols being considered. This is where Model 2, the Bayesian optimizer, comes in. Bayesian optimization uses the predicted results from Model 1 to intelligently decide what to test next. It balances 2 goals, exploitation and exploration. Some of the suggested protocols are green. These are promising candidates predicted to have high cycle life. Others are blue, protocols with high uncertainty, which the model wants to explore further to improve its understanding of the space. These selected protocols are then fed back to the cycling machine for the next round of testing. This loop continues: test, predict, update, until the best protocol is found with far fewer experiments than brute force testing would require. Let's zoom in on Model 1, the cycle life prediction model. The training data came from 41 external batteries not used in this specific optimization experiment. Their full testing data was used to train a machine learning model, resulting in a trained model capable of making early predictions. In the closed-loop workflow, this trained model takes battery cycling data from the first 100 cycles as input. It processes that input and produces an output, a predicted cycle life for the given fast-charging protocol. Now let's take a closer look at Model 2, the Bayesian optimization engine. In this context, every trial is expensive. Why? Because each protocol takes days to test. That alone makes the search slow and resource-intensive. On top of that, battery performance can vary due to individual cell differences. So each protocol needs to be validated multiple times to make sure the result isn't just due to random chance. In other words, we need to make sure we're not fooled by good luck. Because each trial is expensive, we need smart trial and error. That's where Bayesian optimization comes in. Bayesian optimization is essentially a probabilistic model that estimates how different charging protocols might impact cycle life. Based on this, it suggests the next best protocols to test, balancing exploration and exploitation. Exploration means trying different options to unlock new possibilities. Exploitation means refining around the best-known results so far. These suggested protocols are then sent to the battery cycler for testing. Once new results come in, they're used to update the probabilistic model, improving its understanding and guiding the next round of decisions. Now let's revisit the entire closed-loop optimization workflow and think of it as an AI scientist in action. It starts by forming a hypothesis. This is the job of the Bayesian model, which predicts which protocols are most worth testing. Next, it tests the hypothesis by sending those selected protocols to the battery cycler for real-world validation. Then it refines the hypothesis, updating the model based on new results, learning from both successes and failures. This loop continues until it converges on an optimal result: fast, data-efficient, and smarter than brute force searching. Now let's see closed-loop optimization in action through this real-time convergence plot. The closed-loop optimization model converges to a high cycle life region in just 4 rounds. The 3D-axis system represents the protocol search space, and each circle represents a different protocol. At the very beginning, the model assumes that all protocols lead to roughly the same cycle life. There's no prior preference. After the first round of experiments, we move to the next plot. You can see a darker region starting to emerge. This indicates the model has identified an area in the space where higher cycle life is likely. The color bar shows that darker colors correspond to higher estimated cycle life. As the loop continues through rounds 2, 3, and 4, the model keeps updating its cycle life estimations, learning from the test results and refining its predictions. With each round, it gets closer to the optimal protocol. This plot shows the cycle life ranking predicted by the model after round 4. Each circle represents the mean predicted cycle life for a protocol, and the bars indicate the standard deviation, showing the uncertainty in each prediction. What stands out here is that promising protocols are repeatedly validated, while most protocols are never tested or only tested once. This highlights the power of the approach. Instead of spreading effort evenly across all options, the model focuses its resources where it matters most. That means fewer tests, less time, and a much faster path to the optimal solution. So, what did this approach actually achieve? It reduced experimental time by 15 times, from 560 days down to just 16 days. Looking at the bar chart, you can see why. 117 out of the 224 protocols were never tested at all. That's how the model achieved such fast convergence, by skipping unpromising options entirely. And it wasn't just fast, it was also resource efficient. 67% of the batteries were used to test only 21% of the protocols, showing how the system concentrated effort where it counted most. What's even more impressive is that this approach didn't just speed things up. It led to new scientific discovery. The model uncovered a charging protocol that doubled battery cycle life compared to the lowest performing ones. Conventional wisdom says to start with a very high current, then gradually decrease it, assuming this would balance speed and safety, but the best protocols discovered by the AI were unconventional. It turns out, using a relatively high and steady current throughout the early charging phases actually results in better cycle life. This finding challenges existing assumptions and shows how AI can not only optimize, but also advance scientific understanding. So, how reliable is the closed loop optimization model? To validate it, the researchers compared the best protocols suggested by the model, shown as orange bars, with protocols inspired by literature and other baseline models, represented by blue and green bars. They tested each of these protocols on multiple new batteries. The result? On average, the protocols discovered by the model consistently delivered the highest cycle life, confirming that the model's predictions hold up in practice, not just in theory. So, why does this research matter? It goes far beyond just improving batteries. This is a glimpse into the future of AI for science, where closed loop systems can autonomously drive discovery. The process starts with a hypothesis, generated or refined by AI. That hypothesis is then translated into instructions, guiding a robotic system to carry out experiments. These tasks can be broken into two key areas: material synthesis and measurement of properties and attributes. Once experiments are run, the robotic system generates data, which is then fed back into AI models. These models analyze the results, extract insights, and use them to refine the hypothesis, closing the loop. This framework transforms the traditional trial and error process into a scalable, self-improving system, accelerating scientific discovery across disciplines. This closed-loop system has broad applications in discovering new molecules, testing novel materials, and developing new drugs. And when we zoom out even further, the concept of AI scientists opens the door to a much wider frontier. These systems are now being applied to challenges with massive global impact, from regulating nuclear reactions, to solving complex differential equations, to modeling biological sequences through language-like representations. This isn't just a new tool, it's a new way of doing science. The future of discovery is autonomous, intelligent, and already underway.